National Lab, and thank you. I'm presenting about Celeritas for efficient detector simulation on GPUs for Geant 4. I'm the code lead, but this is a pretty substantial team of people working with me from Fermilab and elsewhere, Argonne and Brookhaven and Ben at work. Okay, so diving right in, Celeritas has the primary goal of accelerating scientific discovery by improving LHC detector simulation throughput and energy efficiency. So throughput, we want to simulate more events. Energy efficiency, we want to use less power doing it. Long-term goal is to do as much as possible on the GPU. Our more immediate goal is to focus on EM physics because that's the natural starting point. But we want to leave the door open for more in the future. I'll get to that at the end. So we're jointly funded by the US Department of Energy's Office of Science. It has the Advanced Science Computing and Research Department and the High Energy Physics. So this is effectively a combination computer science experiment and experiment for high energy physics, trying to make their production runs more efficient. So there's sort of a three-pronged approach. The research and development of novel algorithms for GPU-based Monte Carlo is more of the algorithmic computer science aspect, but then turning that research into production quality code that lets us accelerate in production runs by integrating collaboratively with experiments is the ultimate goal. So the way that we got involved and our two motivating factors are twofold. So the first one is the computational demand. So the upgrade for high luminosity means that there's going to be a much larger amount of data coming in, which means much more simulation has to be done. And the current projections are that unless the drastic R&D effort is put in and substantial investments in new computing, the simulation goals aren't going to be met. So that means that there's real drivers for using more hardware that lets us get that higher throughput. So even with some of that R&D being fast simulation, that's going to also require training data. And the only way to effectively train is by using by generating new simulation data. This is kind of a weird place to stand. Should I move over here? I'm sorry. This is okay. Sorry. So even using GPUs, we will have to. Sorry. Fast simulation methods will have to, oh, thank you. We'll have to have training data as well. So you can't just go straight to fast simulation. You actually need to generate new simulation data for that. So at the same time as the demand is increasing, the computational supply is changing. So more and more, we're seeing high performance computing and even institutional clusters adding graphics cards to the mix. So the heterogeneous architectures are increasing. As of 2020 or so, about 30% of the top 500 supercomputers have graphics card accelerators. And the reason for that is that scientific codes can run on GPU with much higher energy efficiency theoretically. So without the GPU efficiency, Summit or Frontier at Oak Ridge, for example, wouldn't be able to reach the exascale and keep within the 20 megawatt envelope for power. So this is also going to get more and more heterogeneous as time goes on because AI and ML are becoming such big topics. They're the source of lots of funding, and they're much more efficient on GPUs than CPUs. So over the next 10 to 20 years, we're going to see a lot more investment, even the next 5 years, in GPUs. So it's just a future that's going to be here, whatever we do about it, AI and ML is going to bring it. There's a problem, though, which is that you can't just take existing codes and put a host device decorator on it and get it to run on GPU effectively. Codes have tried this, and in fact, at the Xscale Computing Project, which is a large DOE effort to advance scientific computing software to run on Xscale hardware, in all the cases that people tried to do that by just taking existing algorithms, they weren't able to do that. So they effectively found that performance on GPU requires a couple of different things. Algorithmic restructuring, so that means reorganizing data, separating the states from the shared data, and transposing loops, for example. Also new numerical approaches, stuff that targets higher compute to memory ratios, which wouldn't make as much sense on just CPU, but makes a lot more sense on the GPU. And then finally, alternative physical models that are more favorable to thread level parallelism. So stuff that works better on GPU when you're operating tasks massively in parallel. And it's not just a matter of porting code. As I said, decorating is never a solid option. It's not brought performance in any of the situations that we've tried. So, and the reason for this is just that GPUs are drastically different hardware, and that means that you require drastically different software. So that takes us into the methods for Celeritas. So some high-level capabilities for our initial goals are we want to have the same effective physics as the Geant4 EM standard physics. So this is basically the simplest fidelity of physics that works for LHC. So it's got a variety of different models that have now been implemented on GPU. There's one or two caveats. So for example, we're using the low energy multiple scattering instead of the high energy one. We're able to simulate geometries on GPU using the VecGeom library, which is co-developed by CERN and Fermilab and is now hosted at CERN. And Celeritas also allows runtime selectable processes, physics options, and field definitions, with the point being extensibility for the experiments. So that way they can change things up depending on their needs. And finally, Celeritas is required to be platform portable. So DOE has experimented with a bunch of different software platforms, in CUDA, NVIDIA, AMD, Intel, and so forth. So we actually can run on NVIDIA, AMD, and CPU devices. And there's an asterisk, which is that right now the VecGeom has some CUDA-specific functionality that prohibits us from running with VecGeom on AMD hardware. So for that, we've developed an alternative geometry engine that right now we're using as a test bed for high energy physics. And I'll just mention it briefly. So it's the Oak Ridge something geometry engine. It's a surface-based navigation, which means that instead of the smallest primitive being a complicated solid, those solids are actually decomposed into infinite quadrics or planar surfaces. And those surfaces are shared across multiple volumes. So Orange is portable, so it works on CUDA and HIP and CPU, and it is effectively still a tracking based on a CSG tree of solids, except now that tree is a little bit deeper because it's now surfaces. It allows us to improve the runtime performance by doing a lot of pre-processing, and because we're doing surface crossings analytically, there's the possibility of avoiding some errors that creep in when you have touching volumetric solid geometries, because you can cross the surface and know that you're on the other side of the surface in a new volume. So it ends up potentially making it more efficient for GPU. Really briefly, we have generic magnetic field propagation. So we have several layers of templating that allow us to switch out integrators, equation of motion, magnetic field type. So right now we have two field types that we have built in. Uniform, so just a scalar or a uniform field overall space, and then a field map that does interpolation over RZ coordinates and returns an RZ composite field. So I won't dive too much into that. So what does a stepping loop on the GPU look like? So our first approach that we took, more out of convenience than anything, was to be able to have a bunch of different kernels that we could compose together in a dependency graph, that dependency graph then linearizes into a loop over different kernels. And we run that loop until all the tracks have been transported. So we want to process pretty large batches of tracks. So we're looking at anywhere from 1,000 to 1,000,000 separate tracks running in parallel on the GPU. And by having these small kernels, we're not only making it easy for ourselves, but we also make it extensible. So there's a box down there for post-step user callbacks that allows users to gather data from the device and the steps. So we can basically add a stepping action, even though we're constrained by some of the GPU complexity. We can still pull data out of the tracks at every step. And this is how, and I'll get to in a minute, but we have sensitive detector integration. So we can actually reconstruct Geant4 hits by pulling the data off the device in that step. So in terms of Celeritas Geant4 integration, this is a critical component of working well with the experiment framework. So we're able to take a simulation that's been set up by a user's JANT4 application. We can read in the physics that they've chosen, the cross sections, the parameters for their field and their multiple scattering and so forth, and convert those into Celeritas GPU objects that we then send over the GPU. With the geometry, we are able to take the in-memory JANT4 geometry representation, loop through the hierarchy, and then reconstruct that on GPU and do a mapping between the JANT4 and VecGeom volumes so that we can correlate device particle states to host JANT4 tracks. The way we integrate into JANT4 is by taking EM tracks and copying over the key data points from them and then killing them on the host and taking ownership of them. Ben has recently added a fast simulation model and a tracking manager that allowed that to be done a little bit more elegantly than just killing the particle in a stepping action. And the other end of the GPU offloading is getting the data back to the CPU. So we actually are able to loop over the users' sensitive detectors and take those volumes that correspond to the sensitive detectors on GPU, record the steps that hit and deposit energy in those volumes, and then copy user selectable attributes like the position and post-step time, or even reconstruct a full navigation hierarchy on the CPU, and then call the user sensitive detectors with those hits. And then finally, because we're working with a variety of experiments, we have to have a pretty broad range of compatibility. So we build against JANT 10.5 to 11.1. And I know 11.2 came out last week, I guess, but we haven't tried it yet. Okay. So I'm going through this faster than I thought, but that's okay because we have a lot of results. And lots of questions, yeah. Okay, so physics verification, it doesn't make any sense to print, say our results are good performance-wise and then have the wrong physics. So we've done some verification and there's still more to be done, but we basically have a pretty good idea that we're doing the correct thing. We're getting the same rough number of step distributions, so we know we're doing the same amount of work on GPU and CPU. And then for some of our tests, we have good agreement within 1% or so between JANT4 and Celeritas. There's some different choices that we've made that may contribute to a difference that we're not entirely sure is an error. There's still a lot of testing to be done. But we have a pretty good idea that at least to first or second order, we're doing the correct physics and we're getting consistent results. An example of this is we took in last February, took a trip out to Berkeley and worked with some of the Atlas folks there and Julianne, who's part of our team, on the Atlas Full Sim Lite test model, which was a test problem done by Stephen Laxnit and Lorenzo Pizzotti. So we took that test beam application, and this was our first real test of integrating into a JANT4 application. So by the end of our integration, so at the end of a week, we were able to get results offloaded onto Celeritas and results back. After some later refinement, where we're able to simplify some of the code and put it into the Celeritas library, it means that effectively it takes only about 100 lines of code in the user application to integrate. No changes to the JANT4 application, no change to the JANT4 itself. So in this problem, we're taking 2 segments of the Atlas tile calorimeter and firing an 18 GeV pion beam at it with no field using a combined hadronics EM physics list. Then Celeritas is capturing the EM tracks, sending them to GPU, running them on GPU, sending the hits back. And we get excellent agreement for the energy deposition with JANT4 and doing a couple other little profiling things. We're able to see pretty good agreement in just tracks and energy deposition as a function of Z as well. So this is a pretty good sign that we're doing the right thing and agreeing with JANT4 as a substitute. So when we've run some performance numbers on these, so most of the performance numbers I'll show in this presentation are based on Perlmutter, which is a pretty common platform for doing high energy physics simulation. It's hosted at NERSC out of Lawrence Berkeley Lab. And their main machine is comprised of a single node that has one 64-core AMD EPYC and 4 NVIDIA A100 GPUs. So the results that I'm going to show are using 4 different simultaneous jobs on that node, each one using a single GPU and 16 threads. So, and the times that are shown here include the overhead of starting up and generating the physics cross sections. They include the JANT4 hadronic physics, the track reconstruction cost, and sending the data back to the host for the sensor detector. So at 16 threads, we actually are seeing a overall speed up of 70 to 90% faster. So this is using all the CPU cores with a single GPU. The CPU cores are busy doing the hadronics most of the time. The GPU is doing the EM. That number, of course, is even higher based on if we use fewer threads. So either, in this application, there'd be no need to do it. But if you're part of a task-based framework where not all the threads are doing simulation at the same time necessarily, you could see some of that higher improvement, greater than a factor of 2 performance improvement. Another really interesting result from this was that even when we're using the CPU version of Celeritas, which we didn't really optimize for, we're seeing a 10 to 30% performance improvement by offloading to Celeritas, even with all the overhead. So that was an interesting result, which suggests that our EM physics does seem to be faster the way that we've implemented it with a tracking loop under these circumstances. So the one other interesting result is that when we first ran this, we only had 1 primary per event, so 18 GeV of energy per event. And that ends up not being enough to occupy the GPU fully. So this kind of demonstrates that GPUs, while good for difficult problems, don't necessarily make sense for the simpler ones. So that's okay, though, because we're targeting the ones that really are computationally challenging and do have a lot of energy and EM particles flying around. So we think that the second number with 64 primaries per event is going to be more representative of an EM, of a LHC workload. So we've also been working with integrating into the CMS software framework. So Soon has done some initial work of putting in Celeritas in there. It's a little bit more complicated because there's a magnetic field involved, and we have to have some code to save that field and load it back in. And set that up through Celeritas. And then there's also a few changes because CMS also uses the custom user track info to do some MC truth type of reconstructions. So we had to change a little bit of code to disable that whenever the track doesn't have that data. When we ran the initial performance results, we were kind of surprised what it looked like. And as we dug into it, we realized that this wasn't an apples to apples comparison, because CMS SW has a bunch of different adjustments to the physics that are done for performance. So they have lots of region-dependent cuts and changes to default parameters. And then they have regions that completely bypass the transport loop and do fast simulation instead. So I'll get more to the results later, but even despite these differences, we've talked to them, and they are integrating Celeritas as an external, and the initial integration is going to be focused on just using this CPU-only Celeritas because it makes software infrastructure a little bit easier to deal with. The maximum speedup that has been calculated for offloading, so Soon basically did a calculation of killing all the EM tracks as soon as they're born and how much faster does it run. And so based on the throughput numbers, he was seeing about a potential speed up of 2.5 to 3. Okay, so because we can't do a fair comparison to CMSSW with Celeritas versus JANT4, what we've done instead for the meantime is done some standalone simulation. So we've taken the CMS run 3 and 4 geometries from CMSSW, exported them to GDML, kept the sensitive detector region so that we know where we have to collect data and send back. And then we've got our standalone testing app for JANT4 called Celergy4. And we're able to enable and disable Celeritas offloading with that, and then we have some results to show from there. So these test problems that I'll show are using 32 TT bar events, so 14 TeV, center of mass energy, from Pythia using the FTFP Bertini physics list. And in this one, just like with the Atlas tile calorimeter, JANT4 is doing all the hadronics, and all the EM tracks are offloaded to Celeritas where they stay. So we're also neglecting any leptonuclear or anything that takes EM particles in and spits hadrons out. We're neglecting all of those. And we've tried the test problem with a couple different field options. One is disabling magnetic field entirely. For reference, the second one is using a uniform field, and then the third one is using that RZ field map. So this is discretized and interpolated in a 900 by 480 grid. And then this last number here is just to give perspective on how much better CMSSW is than the default JANT4 parameters. If you run through CMSSW, it actually gives a factor of 8 higher throughput compared to just running with the JANT4 default parameter. So there's a lot of tuning that's been done there. And in the results, I'm going to show that tuning has been totally discarded. We'll support it eventually, but this is our first apples to apples kind of comparison. So these are speed up numbers with up to 16 threads of an AMD 7532 EPYC using one NVIDIA A100. So the good news is that the reconstruction cost of building up these hits and doing the full navigation history reconstruction and copying the data over from GPU to CPU is a pretty small overhead, which is really good because initially we'd expected that we'd have to implement sensitive detectors on the GPU. And once we started looking at the code, it became obvious that was not going to be trivial. And once we understood the variations that go on within CMS and the different branches and the different tweaks that are being done, it's just not really realistic to have to have two separate code bases, one for CPU and one for GPU. So it really makes a lot of sense to be able to use their SD code, which we're able to do. We've done some comparison of the hits as a function of region and space, and they show that we're basically sending the right amount of energy and number of hits back from the GPU to the CPU compared to pure JANT4. And using the run-3 geometry at 8 cores, we're seeing about anywhere from a 25% improvement to almost a factor of 2 if you don't have a magnetic field. And as I mentioned before, with a task-based framework, that could potentially, you see something like that with using fewer active CPUs during simulation. With run-4, the difficulty with the geometry, and I'll talk more about the geometry later, it means that the performance on GPU is just not as good. If you're not doing much, if you're not sending much work to the GPU, then the performance numbers look great, but obviously you're not going to run one CPU with one GPU. And there's a number of potential future improvements. So we know that our magnetic field propagation still has room for improvement. One of the things that we've initially done in our kernels is to mask out the threads that are inactive. So for example, we actually, we run the Klein-Nishina Compton scattering model on every track that's being active, whether they're gammas or not, whether they're interacting or not. We just exit out of the loop at the beginning of it if they're not actually interacting. So if we're able to use the sorting that we've implemented but not really tested performance-wise in production, then that could give us smaller kernel sizes, which would fit better when we have multiple CPU threads trying to send a bunch of work to be done to the GPU simultaneously. And then also there's still some questions about other more drastic performance improvements like using single precision arithmetic. Okay, so that's what it looked like in the full complicated integrating with hadronics and running through JANT4. So now I'm going to show kind of some speed of light ideal, what it could look like if we have only Celeritas in the mix and if we're running everything on the GPU. So this is a standalone performance of running through a Celeritas app with no JANT4. All we're doing is running the tracks. We're not doing any sensitive detector hit reconstruction. We're just letting them fly and waiting for them all to exit or be absorbed. So this is with effectively 13 TeV worth of electrons using one event per CPU thread, again, using a quarter of the Perlmutter node, so one A100 and 16 AMD cores. And the comparison here in this plot is Celeritas on GPU versus Celeritas on CPU. So it's really an absolute like apples to apples. What's the value of using a GPU versus not? And it actually looks pretty good on GPU. So on the left is the performance speedup, which basically tells us how much we gain by taking advantage of the hardware that's there. So basically, if we don't have GPU, if we have GPUs on the system and we ignore them, we're losing anywhere from 50 to 94% of our throughput, which is means that if you're working with a cluster that actually has GPUs, you really have to use the GPUs, otherwise you're just wasting time. And then on the right side of the plot is the power efficiency, which we've calculated. It's an estimate really, based on the throughput from Celeritas and the thermal power constraints that the vendors have provided for the AMD and the A100 card. So on the bottom axis is these are just a bunch of different test problems. Most of them are pretty simple. And the ones on the far right, the Z and ZFM, those are the CMS 2018 model. This is where the geometry starts to make a big difference. So the orange boxes are with the orange geometry, and the blue boxes are using VecGeom. So VecGeom works really well on CPUs, but because it wasn't really designed for GPUs, there's some performance deficits that it has. So for some of the problems the most complicated problem that we're able to run, which is just test DM3, so a bunch of sandwich layers, it ends up running 2.5 times faster with orange versus VecGeom on GPU. It actually runs the same speed on CPU. I'll get to that in a minute. But this, if that performance trend holds of having a factor of 8 or higher performance improvement versus CPU, then that does translate to over a factor of 2 power efficiency for using GPUs instead of CPUs. And if you're wondering why these numbers don't look as good as if you've seen my previous presentations, it's because we're using a different computer, and this one has more CPUs and they're better. So that affects your speed up numbers a lot. Okay, so the step-dependent behavior is interesting because it addresses some of the concerns that we've had during development, which is basically how expensive are the tails that we have to transport. So again, we're starting off all the particles at exactly the same time and running them. But the takeaway here is that the tail, which is where we have just a few long-lived tracks that are still running large numbers of kernels, lots of step iterations, even though there's a lot of step iterations that have that small number of active tracks, they don't actually take much time at all. So half of the tracks are fully occupied GPU and half of them aren't, but the fully occupied GPU takes more than 80% of the total time. So this is good news because it means that we don't, at least with this problem and the ones that we've seen, have to worry too much about that. It could look even better if we so this is with our masking. So again, with masking, we are transporting 1 million tracks and then running the same kernel with a grid size of 1 million for every single possible model, every single along step process, and so forth. And there are methods that we have implemented but not activated for this problem that could potentially improve these numbers even further. Okay, so I mentioned for the Atlas tile calorimeter that we were seeing performance improvements on Celeritas on CPU compared to JANT4 alone. And these are borne out by some of the test simulations that we have here. So for these problems that we've run, we're seeing that Celeritas on CPU is 50% faster than JANT4. So that means that our GPU to JANT4 throughput is anywhere from a factor of 2.5 to 20 times improved. So there's still some investigation to be done between some of the numbers. So we have 2 separate plots or 2 separate data points, one for standalone Celeritas, one with Celeritas being run just directly offloading the EM tracks. And so there's some performance overhead that we don't understand, but these numbers are hot off the press. And at least based on our consistent results here and with the tile calorimeter for the standalone Celeritas, we could say pretty confidently that we're substantially faster for Jant4 with the same basic EM physics. And these are, by the way, the yellow numbers look much better than the blue numbers. So orange is outperforming VecGeom for the more complicated problems, which I'll get to in the next slide. So I just to touch on this briefly. So this is a grid of two different geometries, orange and VecGeom on the horizontal rows, and then left is running on the CPU and right is running on the GPU. And these are basically pie plots of what part of the code is taking up the most time. So this is, again, TestEM3 is a bunch of planes, boxes that we're firing electrons through. And orange and VecGeom have almost identical performance on CPU as GPU, and even down to the fact that we're seeing the amount of work that's being done in physics is identical for the two of them. And there's the green bar is the geometry plus physics, which is the along step propagation, because that has to that is both it's the combination of the field propagation plus the multiple scattering, which also involves safety distance calculations and so forth. So they agreed great on CPU. They're both 40% faster than the problem in Jant4, but there's a huge disparity when we run on GPU. So the orange profiling on CPU and GPU are fairly comparable. Physics is a little bit faster, and it's about 10 times faster overall on GPU than CPU, but it's still, again, 2.5 times faster than VecGeom. So we're seeing that the geometry for VecGeom is much more expensive on GPU. So that's really, this is more about what our potential growth is for some of the more complex problems, rather than there's a problem with VecGeom. So the results, even though we can't use this simpler orange geometry on the real detectors like CMS, the fact that we can see a factor of 2.5 improvement on these fairly difficult problems, moderately difficult, still fairly simple, that gives us a hope that whenever we can run the more complicated detectors with a surface-based model, we'll also see similar performance gains. Okay, so finally, I think this is the last one of the slides for the results. We have power efficiency, which is really important for viability of data centers going forward. So again, the motivation for using GPUs as opposed to CPUs is the thermal efficiency. And so these are estimates using the thermal design power and Celeritas output. And the takeaway from this plot is that GPU does consistently show higher energy efficiency, much more substantial than CPUs. So the CPUs are the solid boxes and circles at the bottom. Circles are the Jant4 standalone. The boxes are Celeritas. So there's a huge performance or efficiency disparity between the Summit CPUs, which are IBM, and the AMD ones. And then there's also actually really substantial difference between the Frontier, Summit, and Perlmutter GPUs. So Perlmutter is again the AMD, Perlmutter is the NVIDIA A100, which is almost twice as efficient as the V100 in our testing. Summit is much more efficient than CPU still, even though it's a generation older. And then finally, and kind of disappointingly, but not too surprising based on what we now know about AMD, is the AMD efficiency for Monte Carlo programs is not great. It's worse than the V100s, and effectively we've talked to AMD, and there's some architectural differences, especially with regards to caching, that make the A100 much more suitable for things with random access data patterns. So based on what we've seen, I would definitely recommend not buying AMD, but don't tell Oak Ridge I said that. Also, in terms of price and performance per dollar, so the A100 is about $10,000, and the EPYC is about $2,500. So it's, in terms of performance per dollar, about the same, efficiency per dollar, about twice as much. Okay, so some concluding remarks. ongoing work. We're still working with a variety of experiments on collaborating and integrating Celeritas into their framework. So CMSSW we've been working with and are on track with that. Ben's been helping us with Atlas and Athena. And then we've also been working with some students as well as incorporating them into Celeritas and using it for their research as well. There's still obviously a lot of work to be done with verification and validation, but the good news is that now that we can do direct offloading with JANT4, it means any JANT4 verification validation problem, it becomes a Celeritas V&V problem. So it should be pretty easy to test Celeritas on a variety of important applications and see how it performs in terms of physics viability. And then finally, optimization and geometry. So this is the pie plot effectively for, I showed earlier, TestEM3, and this is for CMS 2018. And 96% of the runtime on GPU is in the geometry heavy routines. And that's compared to the profiling layout for JANT4, where you see, sort of flat, every routine takes about the same amount of time, means you can't really optimize one piece and get the whole program to go faster. This is great because we only have one place that we have to optimize. Now, it's geometry, it's not a small piece, but it means that we really just have to, for the moment, focus on geometry performance, and that will give us big gains in our overall GPU performance. So besides the geometry, there's potential comparisons that we have to, well, there's still performance comparisons that we want to do for doing GPU device sensitive detectors versus offloading back to the CPU. Orange navigation, of course, as I mentioned, for geometry. And then as I also mentioned, instead of doing masking for these kernels, we are able to, but have not yet tested sorting tracks and different strategies for improving the performance by having smaller GPU kernels. So the future of Celeritas, so we're designed for three things: easy integration, extensibility, and performance. So we want to integrate well into JANT4. So we're talking with, we're here for the R&D evaluation on Wednesday and Thursday. And our goal is to do more incorporation into JANT4 as an accelerator for HEP applications, and still work with the HEP experiment frameworks directly to get Celeritas in there. We're designed to be extensible, so we're in the process of considering extensions to Celeritas beyond EM physics. So for example, we've got plans for optical photon simulation on GPU, and then potentially even adding more physics like neutrons and leptonuclear and so forth to be able to gradually do more and more work on the GPU and potentially improve the overall throughput for JANT4. And then we're still, we're designed for performance. So there's still a lot of work to be done here. Without changes to the external interface, we're able to do a lot of internal tweaks. So that means that integrating now, the interface will still stay the same. We could still see performance gains for downstream applications just by our internal changes. Based on some of the numbers that we have, we expect the surface-based geometry, which VecGeom is developing a surface-based geometry, as is Oak Ridge for the nuclear applications. So we expect that to be much faster for complex applications. And finally, it works well on CPU and it works better on GPU. So again, just to summarize some of the important numbers, 100 lines of code is all it takes to integrate Celeritas into application. No modifications to a JANT4 installation. You just add a callback at the end of the event, a tracking simulation manager, and a couple of options to tell it what data you need for your sensitive detectors. For some of our test problems, we've seen a factor, an 80% full simulation speed up, including the Hydronics and SD hits using an A100 with 16 cores. With pure EM physics, there's a potential of having anywhere from a factor of 2 to 20 times improved throughput using GPU compared to CPU. And then finally, there's a potential of much higher efficiency. So on TestEM3 with orange geometry, compared to the JANT4 CPU, Celeritas on GPU has a factor of 4 improvement in performance per watt. So we've released version 0.4. It's available on GitHub, and there's a large group of people who've contributed. I'd like to thank, as well as the Oak Ridge computing facilities and LBL facilities as well, and our sponsors at SciTech. I'm sure there are lots of questions, so I'd be happy to entertain them. Thank you.
Thanks a lot, Seth. That was a very comprehensive update. Lots of interesting figures to dig into there. So we can certainly open up to questions now. Attila? Yep, go ahead.
Yeah, I'm filled with questions, but let's. This must not be any news here to anyone, but I'm a little bit disappointed by the some of the numbers, the performance numbers. So you showed some plots of what the results, or what the performance results are, but I wonder. I imagine you had to profile these jobs on a hardware level in a bit more in detail. So what do the NVIDIA tools tell you? Where are you losing performance?
Is Brett active? Yeah. Okay. So there's the big one is so we lose. Well, obviously, Monte Carlo on GPU is memory latency driven. So it's not just pulling data from the GPU into the registers. It's also the fact that the access patterns are very, very random, and you're constantly pulling new data in and out depending on where you are. So we're latency bound. Another factor that reduces our performance is the occupancy. So there's a lot of temporary data that gets used as registers, and that limits the number of warps that can be run simultaneously. So we've done some profiling, but it's latency.
Yeah, because if you go to the Atlas results, like page. This one. I was a bit surprised. So first off, I don't fully understand. Primary. What does primary mean here exactly? A part scatter?
No. Sorry, this is one pion per event.
Okay.
Yeah. So this is an 18 GeV pion beam, and so
pretty low activity.
Yeah, very, very low.
Okay. That still gives me a little bit of hope then. But at the same time, just with a single pion, you seem to be fully saturating an A100 with 8 events at the same time. So this means that at that point, you cannot launch any more threads.
Well, it's not so much that we're saturating it as much as we're running into the we're just entirely on overhead. It's
This is what I expected. That
yeah.
Because of whatever problems, the GPU doesn't take more work at that point. But okay. I'll let other people. Right, but I thought that those giant threads are all working on different events. Is that not the case?
Yeah, that's the case.
Okay.
Yeah.
Yeah, but it's really a matter of we're just not giving the GPU enough work to do, and so it takes a lot of time to the cost of transferring stuff over, running the kernels, and transferring stuff back is just not worth the.
Well, I think the next was a question from Andrea.
Yes.
Yeah. Hi, Seth. Thanks a lot. This was very, very nice and very comprehensive presentation. I have several questions as well. Maybe just starting with one very basic thing, which is, I mean, you showed, if I understand correctly, you showed some throughput speed ups for let's say, for the full workflow, and then for what you call the speed of light, which is just electromagnetic part. Now, my question is, you've not shown a profile. I mean, how much in a typical full Giant 4 workflow is the electromagnetic part? Rephrasing, what is the maximum throughput speed up you can expect by just speeding up the electromagnetic part?
Yeah, so I went pretty quickly through it, but this is the number that Soon has run on CMS. It's problem dependent, obviously. But for CMS, it looks like that number is about 2/3 of the time is spent on EM track. So that means that you could accelerate it potentially up to a factor of 3 if
wow.
the GPU transports instantaneously.
Okay, great. So 1/3 is the rest. Thanks. This is very nice. And if I may ask already a very different question, which is it's related. It's partly related to what Attila said about the performance, but it's also about your performance per watt at the end. My question is, okay, is vectorization essentially. So on CPU, do you manage to get any speed up through vectorization, or could you get that? Because I mean, my question is, it's related a bit to the GPU performance, because my question is how much lockstep processing you have, and if you do have a lot of lockstep processing, maybe you could have SIMD speedups as well. But it's also related to the performance per watt, because in the end, I mean, if you compare a GPU to a CPU where you have no vectorization, is a different thing than if you compare as a GPU to a CPU where you do have vectorization, where you might get significantly higher throughput for the same watts.
Yeah, that's a good question. And the way that GPU vectorization works isn't really the same as the way it does on CPU. In fact, even on the newer NVIDIA hardware, individual threads can have separate instruction counters. So you may have multiple threads in a warp executing different instructions and using different data. So it's not really that all the threads are doing the same work at the same time. It's that the GPU is able to do enough work quickly enough that it's faster. You know, it would be faster if we were doing exactly the same operations at exactly the same time. But the way that CUDA is set up is we don't have to do it that way. And so that's what allows us to make Celeritas work on CPU and GPU, is we can use sort of single-threaded, independent track workflows, and then just let CUDA run all the threads and do its own thing. So we don't have any explicit vectorization in there. What the CPU, the vectorization we have on CPU is we have a vector of tracks, and we can farm that out to OpenMP, where it'll just loop over chunks of those tracks. And so it's not really vectorized in the sense of using SIMD. It's more of you can operate on that loop in chunks.
Thanks a lot. I'm sorry. I mean, I know that CUDA does allow you. I mean, it's what I often say, that programming CUDA is easier than programming SIMD, exactly for what you explained. But my question is, do you think you could actually restructure your code in such a way that you could actually get more lockstep processing and more threads in a warp to do exactly the same thing, and then also be able to exploit vectorization? I think it's very difficult, but
yeah, I don't think that's the case. There's just so much divergence in these algorithms that there's going to be very few places where you can guarantee that all the, especially the way that we're doing it with the masking, that almost guarantees that we won't have 4 consecutive tracks doing the same thing, because 1 or 2 or 3 or maybe even 4 of them are going to be idle. There is a potential for vectorization in a couple of key performance heavy places. So I think for like the magnetic field driver would make a lot of sense to do SIMD vectorization on the field calculations, for example. And that would be one place where you could really just put the vectorization in one place and not have to worry about refactoring the entire code, and potentially see a big performance improvement there. Same thing with some of the geometry kernels. It's possible that when we're doing these quadrant calculations, we might be able to vectorize some of that work as well.
Thanks a lot.
Hmm?
The comment on SIMD vectorization. I mean, we have done a long R&D for years, and we have shown that indeed you can apply SIMD to specific algorithms like magnetic field or special physics processes, but overall you will not get something more than 10%, 15%, and you have to pay the price of doing a lot of memory copying to enable vectorization, because it doesn't come for free. So I mean, we cannot, expect just this kind of code refactoring to also provide you with the tools that you would need for vectorization. So it looks like the simulation code is intrinsically non-vectorizable in this perspective.
And the big benefit for CPU, actually, one of the reasons that I think Celeritas is much faster is because improving efficiency on GPU or getting your code to run on GPU kind of requires restructuring the memory so that you're operating on as much of the same data as possible in a short time frame. So we've had to do a bunch of data reorganization that effectively improves cache coherency. And so we don't have to do as much. We can operate on smaller chunks of data at a time. So that potentially gives us a much better improvement. It's not the same as vectorization, but that is one of the, I guess, related aspects that's interesting for the work.
Okay, thanks. Attila, yep, back to you.
Yeah, I actually wanted to ask exactly on this, on why you think the CPU code is significantly faster than G4. So you, I would have thought that maybe you don't even run the exact same, well, that you run fewer calculations in Celeritas. But so are you claiming that it's not mainly that, but like a better cache coherency?
That's what I think. Yeah, there's a lot of overhead in JANT4. There's a lot of abstractions that make JANT4 extremely flexible that hurt instruction caching, memory caching, everything. So we're able to lower the overhead to very small numbers and potentially improve performance that way.
One example is just using, compacting the physics, what G4HEPM does, okay? And it was shown already in Atlas, for instance, that it brings just by doing this, just eliminating all the overheads, the processing calling, all these virtual calls and stuff. And the fact that the work is done in a much more compact way, that you just get benefits immediately.
Sure, but we saw percentage improvements, not factors. Okay.
Yeah, that's actually a good point because we are doing some algorithmic differences. So with JANT4, each process before the G4 gamma general, right? Each process had its own physics length, and each one had to sample it independently and then do a post-step do it. In Celeritas, we take the sort of approach that we had for the nuclear engineering code, and we pre-calculate the cross sections, do one simple distance to collision, and then sample the process after we collide. So our pre-step on CPU takes about, I guess, like 20% of our overall time. The pre-step is what does all the cross-section calculations.
Carry on, it's just fine.
So since you mentioned that you want to enable the users to plug their own code in, how is that meant to happen? So how do you do it now, and how do you want to do it in the future?
Yeah, let me go back to, okay, so I breezed through this, but the stepping loop is a bunch of different CPU virtual classes that we call action interfaces. And each action interface is you call it with a chunk of a state. So one per JANT4 thread, as well as the shared data. And that can launch one or more GPU kernels. So through that host virtual device, we can have a lot of flexibility in how we composite the different kernels that we have. So for example, a long step box there has two different along step methods. Originally, we only had a single along step. Users could potentially add an along step method that applies only to one region or one particle type, or different ways of filtering and applying new kernels to just the tracks they care about.
I guess my main question here is that is the user expected to plug in a kernel of their own, or are you relying on virtual functions or function pointers? Yeah.
Yes. So in order to do anything meaningful with the device data, they're going to have to plug in a kernel. So for new physics, but we do have a lot of abstractions that make new physics pretty simple to write. So we've got, we had a student put in a single Coulomb scattering, and he did it in a month or two. So we have abstractions that make it pretty easy and stable to do that. That's for physics though. For doing stuff with step data, we do have a interface that works with just CPU virtual functions that copies all the data from GPU back to the CPU for you. And so if you're just doing if you're interested in step data, like a step callback, that you can write only CPU code and still do something useful with it.
To clarify, I'm okay with this answer, saying that that it's pretty impossible to do user code in the stepping function efficiently. The user would have to somehow actually inject their code into your generated code, recompile stuff.
Yeah.
And I was just wondering if you went down that rabbit hole or not.
Yeah, no, we've originally we said our expectation was no user extensibility, but the way we've kind of evolved is that we think it's more and more possible. And I think, depending on the complexity of the user code, it could be, as simple as a few lines of C++ code and then a couple of wrapper functions that you write in a .cu file. So it could be pretty easy.
Okay, thanks. Andrea, I think you've got a fresh hand, yeah?
Yes, it's a fresh hand, thanks. Thanks, just a completely different question. You mentioned this urban MSC on slide 8 and then slide 15. Now already I have no idea what this is. If you could elaborate, and especially on slide 15, slide 14, sorry, you say something about most significant disagreement remain in urban MSC. You said something during the talk, but I didn't really understand that.
Yeah, so this is the multiple scattering model. I think Soon can probably answer this better than I can. But it's the low energy multiple scattering model in JAMP4 with I think like a safety based step length limiter.
I can't hear. Sorry.
All right. So urban MSC model is valid up to 100 MeV, and it also interacts with geometry in JAMP4 with especially safety calculations. And the Celeritas actually remove the safety features. But crossing there are 3 different models, the boundary crossing model there. So one is the safety, using safety. The other one is a simple, and another one is what they call the boundary distance. And the high energy model is one the BI models, which actually we need to add in principle. But right now, the urban MSC actually can approximate high energy model 2, so which is actually same for that. Yeah, so that's sort of the overall implementation features. So do you have any particular question on multiple scattering?
No, I just wanted to understand if it's a model that I mean, is this something that still needs some work on? I mean, it's like, do you plan to improve this urban? I mean, if I understand that there is this agreement, do you plan to actually improve this urban MSC, or do you plan to use a different model to do the same kind of physics? Or
so urban MSC is sort of a ready parameterized model. So there is for example, Kudesmith-Sanderson is a much more accurate but more computationally expensive. So we can explore that. But the MSC model itself is one of a complicated the EM physics model, so which actually a lot of room to, I think, optimize. So which is, I think, one of our also the item to explore. And yeah, but the point here is we can sort of adopt other MSC model also easily. So that's how this action basically decompose for different, I think, functionalities.
Yeah, so we are planning on finding and fixing this model. We've spent most of our validation time so far on just the main discrete models and not so much on the urban MSC. So we still have some testing and verification to do. We have verified certain parts of it, and we've also found certain small bugs in Jant4's implementation that we're not sure how important they are, but we're still trying to understand exactly where the difference is and why we're seeing the disagreement.
A lot.
John? Yep.
One thing to mention is that people who want to know more can attend the Jant4 internal review. It is open. It will also, where the prototype, which is more authors from CERN, adept, will also be discussed. There'll be a chance to ask more questions and understand things more in depth. So I didn't really want to get too much into the details beyond saying that and inviting people at the moment. There will be plenty more, a lot more than we can scratch in an hour.
Is the review about how to integrate it, all this code into Jant4 directly, or what's the?
It's an internal assessment, I would say, and what the state of the R&D is and how to proceed. Because both are blessed R&D projects.
Which should certainly give people a lot more scope for discussion. Okay, any other questions that people want to ask today? With that, I see Marcus, you put your hand up, so I'll let you.
Yes, thanks.
Go ahead.
So I have a question that is a little bit less technical. So there are two slides that mention basically directly or indirectly cost, slide 24 and slide 28. And in slide 24, you have an estimate of the cost of the GPU versus the CPU, which is a factor 4.
Yep.
And on the slide 28, you have a speed up for the full simulation of 1.8 and the performance per watt by factor 4.
Mm-hmm.
So while this work, of course, is extremely important for our community because we are getting HPC resources with GPUs, whether we want it or not. So we have to do that. But with it's based on these numbers, if it comes to simulation work, is it an economic feasible decision to buy GPUs?
Well, that's a complicated question. So I only ran these basic rough numbers, and again, the performance per watt here is if we could do all the physics on GPU. It's not necessarily what I haven't run the numbers for what it looks like for using it in tandem as part of a full simulation. I think you got to the main point, which is they're coming whether we want it or not, and so we have to continually pursue doing more work on GPUs, and this is kind of the first step in that direction.
Yeah,
I think once we get more physics on there,
the work in any way, I think it's
Oh no, I didn't get that.
Because of the need that we have to use HPC systems to the full extent. So there's no simple answer then right now about.
It's a complicated. It depends on a lot of things, and there's a lot of stuff that we're neglecting in this performance per watt. We're not taking into account the cost of the node hardware and the cooling systems and whatever else.
No one has done realistic sets of events on a full geometry.
Right.
At the moment, they're only projections.
Yeah. So we want to have, if we want somebody to build us a little computer that has one node with 2 AMD epics and one with 1 AMD epic and an A100, that something like that, where that's the only way to have a realistic comparison, I think. But this is a projection that I think is a good enough.
And then also take the lifetime of a system into account because of the power savings.
Yep.
Only show up due to over the full lifetime. I think it would be really good if people who work on GPUs and do these measurements would also participate in these cost working groups that exist on the fabric side. Because now this is more all driven like, yeah, GPUs are interesting. But at some time when we really have to decide whether we buy CPUs or GPUs, then this becomes a really important issue.
Yeah,
well, thanks for your answer.
Oh, great question. Thank you. Andrea?
Yeah, just to add very quickly on what Marcus said, that I agree that it would be really nice to integrate this kind of work. More than the cost model, I was thinking of the HyperX benchmarking that, as Graham said at the very beginning, will make a presentation, I think, at this forum in February, because there we are also doing tests where by incorporating the workloads in containers and then doing a lot of measurements. Because actually my question here is, you said this is based on the specs. It's not based on actual measurements, or what is it?
Yes, that's right. I mean, there's no way to get that data unless you plug a kilowatt into the wall. And
no, but exactly this is exactly the kind of test that we are starting to do, and that we plan to do much more in the HyperX benchmarking working group. So I think it would be really interesting also for you to attend this.
That'd be great. Yeah, if there's a way to collaborate and actually use Celeritas as part of that test bed, that would be really valuable to everyone.
I think that would be very interesting.
But just to jump on this, benchmarking, very good. I fully agree. We have to do it. But when it comes to deciding what a given computing site is buying, everybody wants to do machine learning and AI. They will be buying it because it's not a contention that GPUs are way more efficient and performant for that. So even if our stuff is not super efficient, computing centers will be buying these, whatever. Now, for the computing sites that we operate, for instance, with the large LHC experiments, yes, there we have the entire picture of everything that we want to run on them, and then we can make the full calculation of what makes more sense to buy for an HLP, a high-level trigger. But yeah, computing sites, they will be buying these things. As long as I'm speaking. Floating point precision.
Because Liz wants to get in.
Floating point precision, which I know it's a very deep kind of worms.
Well, before we go there, can I just complete a thought? I guess.
Yes, please go ahead, Liz. Yeah.
I was going to point out something similar to what Attila said, but for the reconstruction, even we can make use of the GPUs. So I think that we've always known simulation was the hardest one, right? So, anything we can get at all on GPUs with simulation is a plus as far as I'm concerned. And the benchmark, just making the comment that, what you should buy today should really be based on how much better throughput you can get with a particular architecture over another. That's always been the metric, right? And if we just consider GPUs another device that adds to the architecture of the computing that's about to be bought, and see what it does to our throughput, I think that's the true metric for what you should put your dollars into. So it really requires a lot more work on the software side to make sure that those things get into production, and therefore once they get into production, they get into the benchmark, right?
Thanks, Liz.
I have maybe some good news on the power. I mean, if I understand correctly, you used the TDP of the cards from datasheet, right? For Adept, I don't know for Celeritas, but I'm extremely sure it's the same, since we are not fully maxing out the device. We're not using the tensor cores. We're not using RTX cores, whatever it is. I see on our stats, which you read from some NVIDIA tools, so I don't know if they can be trusted, they were using 100 watts.
Yeah, I've seen the same thing for Celeritas on
So the factor is that you compute in terms of at least power efficiency, they might be a factor 3 higher.
Yes. Potentially.
We're not maxing out the device because we can't just get enough work from Gen 4.
Yeah.
But that's maybe good news, right? The device is doing something, but at a third of what you see in the data sheet.
Well, the other thing, like with Perlmutter and some of the other OLCF machines, is that you can't, the thermal capacity of the node as a whole is also limited to less than the sum of the thermal power from the different cards in it. So we can't, like on Frontier, for example, we can't run all 6 or all 8 MI250X GPUs at full throttle and the AMD, and because there's just too much power output, and so it has to throttle them back. So there's limitations there. But yeah, I have seen the same thing with Celeritas and on our little in-house test beds, and I don't want to be too optimistic, right? We could see better numbers, but we're not going to know until we do what Marcus said and actually run some, plug it into the wall and see.
Great. Tella, did you want to talk about precision?
Yeah, we shouldn't spend the night here on this, but so did you guys make any preparation in the code to even be able to evaluate what just single precision might do to the precision of your output and your performance?
Yep, I'm glad you asked. Yeah, we actually do have a configure time parameter that lets you switch between double and single precision, and this also could potentially let you do the differential operator analysis. Where you can potentially propagate a uncertainty along with there, because everything in Celeritas is templated, and we don't use hard-coded double anywhere really. So we could extend it to real, we could extend it to double, we could do other things. We haven't successfully really run a single precision test because of there's one or two things we need to try first, but effectively we're seeing step limits that are small enough to result in no change in the actual position. So we need to do some twiddling with our propagation.
So Attila, we have done some single precision test level of the geometry, like in a depth in the past. We saw some 40% improvement on an RTX on a consumer card. Point is that to use that at full simulation scale is delicate in simulation because you require double precision in parts, in several critical parts of the simulation. So you cannot generalize it everywhere, like changing the type, like Seth was mentioning, which can be done, of course, but now then you discover things are not working anymore, and then.
But as we all know, the holy grail here is trying to find a GPU that is not as expensive as the A100 or the H100.
I think one point that was not discussed that comes out immediately from the slides of Seth is, how much the picture can be changed if you manage to improve the geometry and make a surface model on top of that. Because, now like 95%, as you saw, is bound by geometry. So if you manage to remove that bottleneck, the whole thing can change. So yeah, the picture may be very, very different in 1 year from now.
Excellent. Okay. I'm conscious of the fact that there's another meeting which is of interest to our simulation folks that starts in a little over 10 minutes. And those of us in the room will have to disperse and get back to somewhere where we can join the meeting on Zoom. So I think unless there's any other burning questions. No, I see movement towards doors and things like that. So that sounds like it's an excellent place to stop. So my thanks to Seth and to everybody who contributed to the discussion. And just as John said, a reminder that there's going to be plenty more discussion about this topic in this week, and that's an open meeting that anybody who's interested in can go along and discuss.
Sorry, Graham, just to also say for people at CERN, obviously the Celeritas team and ADEPT team are working together. So if anyone wants to just have chat over coffee, we are available. So just drop one of us a mail and we can set something up.
Sounds great. Okay, thanks very much, Ben. All right, I think we'll close the meeting here. Thanks again to everybody, and wish you very happy holidays, and see you again in the new year. Bye-bye.
Thank you. Bye-bye.